There's this invisible force humming inside your walls, powering your screen right now and pretty much running our entire modern world. It's called alternating current, or AC. And in this explainer, we're going to pull back the curtain and really get to know this fundamental form of electricity.
So here's our roadmap. First, we'll dive into the historic current wars to see exactly why AC won. Then, we'll figure out how you even measure a current that's always changing. After that, we'll meet the three main personalities of any AC circuit, see what happens when they team up, and finally, we'll get to the grand finale, the transformer, the device that really makes our power grid possible.
All right, let's start at the beginning, with a huge decision made over 100 years ago that basically shaped our world. It all came down to a big fight between two different types of current.
Okay, so on one side you've got direct current, or DC. Just think of a battery. The electricity flows out in one steady, straight line. It's like a one-way street. But on the other side, you've got alternating current, AC, which is what's coming out of your household outlets. This current is literally flipping its direction back and forth 60 times every second.
So why on earth did this shaky back-and-forth current win the war? Well, it really boils down to efficiency. You see, AC has a superpower. Its voltage can be changed, like super easily using a device called a transformer. This means power plants can crank the voltage way up to send it hundreds of miles with hardly any energy loss, and then step it way back down to be safe for your home. Back in the day, DC just couldn't do that.
Okay, so if this current is constantly going from a peak down through zero to a negative peak and back again, how do you give it a single number? I mean, if you just took the average of the whole wave, it would be zero. That tells you nothing. So there has to be a smarter way to measure its real power.
And that smarter way is called the root mean square value, or just RMS. The best way to think about it is as the effective value. It basically answers the question, what DC voltage would give me the exact same amount of power? So when your wall socket says 220 volts AC, it means it has the same power-delivering punch as a 220-volt DC source. It's just a brilliant way to make AC and DC comparable.
And this is why it's so useful. Because we use RMS values, the good old power formula that everyone knows, power equals voltage times current, works perfectly for AC too. No new complicated math needed. It makes everything incredibly straightforward, just as if we were working with simple DC.
Now, things get interesting because AC doesn't treat every electronic component the same way. To really get AC circuits, we need to meet three main characters, and each one has its own very distinct personality.
First up, we have the resistor. This is the simple, no-nonsense character of the group. When AC flows through a resistor, the voltage wave and the current wave are perfectly in sync. They rise together, they fall together, they hit zero together. We say they're perfectly in phase.
Next, we have the inductor. Think of an inductor as being a little stubborn. It's basically a coil of wire, and it builds up a magnetic field that hates change. So when the AC voltage pushes, the current takes a little moment to get going. The end result? The current always lags behind the voltage by a quarter of a cycle, or 90 degrees.
This special kind of opposition that an inductor puts up against AC is called inductive reactance. And what's really cool is the faster you try to make the current change. In other words, the higher the frequency, the more the inductor fights back. Its reactance goes up.
And our final character is the capacitor. This one acts like a tiny, super fast charging battery. Now think about it. For a capacitor to build up voltage, current has to rush in first to charge its plates. The voltage only builds after the charge is there. This means the current gets a head start, leading the voltage by 90 degrees. It's the exact opposite of our stubborn inductor.
So naturally, a capacitor's opposition is called capacitive reactance, and it's opposite in another way too. The higher the AC frequency, the less time the capacitor has to fully charge up on each cycle, which actually makes it easier for current to flow back and forth. So its reactance decreases as the frequency goes up.
And here is one of the coolest, most counterintuitive facts in all of electronics. Unlike a resistor, which burns up power as heat, a perfect inductor or capacitor consumes zero net power. They're like perfect energy managers. They just borrow energy from the source for half the cycle and then give it all right back on the next half.
So, what happens when we put all three of our characters, the simple resistor, the stubborn inductor, and the eager capacitor all into the same circuit? Well, this is where the real magic happens.
In a circuit with all three, the total opposition to the current is called impedance. It's a combination of the resistor's simple resistance plus the effects of the other two.
And as you can see from the formula, the inductor and the capacitor are in a constant tug of war. Their reactances are literally subtracting from each other. This leads to a really interesting question, right? What happens at that one single special frequency where the inductor's push is perfectly canceled out by the capacitor's pull, when their reactances are exactly equal? That special condition is called resonance. It's this magic moment where the two opposing forces, inductive and capacitive reactance, completely disappear. They cancel each other out, and it only happens at one very specific resonant frequency.
And the result is powerful. At that exact resonant frequency, the total opposition, the impedance, just plummets to its absolute minimum. With almost no opposition left, the current at that one frequency can flow like crazy. This is exactly how you tune a radio. Every station is broadcasting at a different frequency. When you turn that dial, you're adjusting your circuit's resonant frequency until it matches the station you want. And boom, that signal comes flooding in at maximum strength while all the others are pretty much ignored.
And that brings us to the grand finale, the one device that truly made AC the undisputed champion and makes our entire power grid possible, the transformer.
So how does it work? It's a beautiful principle called mutual induction. First, you run AC through a coil of wire. Because the current is alternating, it creates a magnetic field that's constantly growing, shrinking, and flipping. Now you place a second coil of wire nearby. That pulsing magnetic field from the first coil cuts across the second coil and induces a brand new AC voltage in it, all without the two coils ever touching.
And here's the genius part. If that second coil has more turns of wire than the first, the voltage gets stepped up. If it has fewer turns, the voltage gets stepped down. Simple as that. But because you can't create energy from nothing, when the voltage goes up, the current has to go down. And when the voltage goes down, the current goes up. It's that trade-off that is so critical for efficient power transmission. So let's wrap this all up. We saw that AC is the current that's always changing direction, and we learned how RMS values make it easy to work with. We met our three main characters, the steady resistor, the lagging inductor, and the leading capacitor. We discovered that at that magic frequency of resonance, they basically get out of the way and let the current soar. And finally, we saw how transformers use this amazing trick of mutual induction to change voltage and power our world.
You know, AC absolutely won the war of the currents to build the grid of the 20th century. There's no doubt about that. But as we look to the future, with solar panels, huge battery banks, and all of our electronics, which are all inherently DC, it really makes you wonder, what kind of current will truly power the 21st century?